Some of this will actually be review. And I always forget how much is in the grade 11 compared to the grade 12, because at one time there was no coefficient of friction in grade 11, and there was a move of some kind, and I always get confused. Yes, Quinn?
Did you give us the right papers?
Does it say physics 30S and friction on it?
It's a scratch.
Well then no. Clearly the answer is no.
It says the nature of friction.
Is there something wrong with this one that says the nature of friction on it?
Well, I don't know, we not even know.
Something that says physics.
Okay, so let's begin. Now you do have a handout. What I did was basically, I've got this handout and I've created notes from it. So what you're about to see up here is basically the highlights of what you got right here. So you can deal with this however you want. If you want to write stuff down, you can. If you want to sit back and relax, you can. I'm going to be posting the PDF of this very soon. If there's little important things you want to jot down, that works for me too. Whatever works best for, you. Got the hiccups. What is friction? Right there. What's friction? It's a force that resists motion. It involves objects that are in contact with each other. There must be contact. If I throw a baseball through the air, is it in contact with anything?
Air.
It is the air. That's what causes air resistance. And if you were in a space shuttle, you would know all about that, because as it reaches the air, there's a lot of friction and it heats up, and, well, sometimes it's disastrous consequences, right? There is actually not a firm understanding of friction, the theory of friction, if you will, how it works. There are some hypotheses, it's a hard word to pluralize. They think that an object deforms a surface and vice versa. So in other words, when you've got a book on a table, the book actually makes a little sort of hole in the table, depending on how heavy it is, right? And then a plowing force is required to move the object over these deformations. In fact, it's going uphill. There's a bit of a uphill ramp type of thing right there, right? The other theory is that irregularities interlock and offer resistance to movement. So in other words, when you've got that book on the table, it's not perfectly smooth. It's in fact, it's rough, right? And so it sort of has to sort of bounce over those kind of things. And in fact, sometimes those little irregularities, those little bumps will come off. That's the whole idea behind sandpaper, isn't it? Right? As you smooth the wood, the sandpaper gets smoother as well, and you create, well, dust. So there's a couple of ideas about friction. This is something that you do need to know. Starting friction is the maximum frictional force between stationary objects. If I go to move something, the amount of friction is equal to it's called starting friction. It's always the maximum amount of friction. Once you get objects moving, it's a little bit easier. This is known as sliding friction, the frictional force between objects that are sliding with respect to each other. Now, generally, humans invented the wheel. We don't really know when, I suppose, but it certainly made pushing things around a whole lot easier. Is rolling friction one of those two things, or is it a third sort of thing? What do you think?
Starting friction.
Rolling friction is a type of starting friction? Why do you say that?
I don't know, maybe it's because as you're rolling a wheel, and every point that touches the ground is
It's starting new kind of thing. You're absolutely right, actually. The idea is that rolling friction is a type of starting friction, and the friction itself is actually between the surfaces inside the wheel, not so much the wheel on the ground, right? It's generally heat that causes deterioration of things like rubber wheels and stuff like that. Generally, we will ignore rolling friction. It's hard to deal with. Every situation we're going to be in is going to be starting or sliding. Even if it is rolling, we're just going to consider it sliding. Okay? So, which one is greater? Starting friction. Sliding is always less than or equal to, actually. Sometimes they're equal to. Okay, some properties of friction. Friction, and this is right there. You definitely do not need to copy this down. It's like right there on page 2. 1, 2, 3, 4, 5. Friction acts parallel to the surfaces that are in contact. and in the direction opposite to the motion of the object, or to the net force tending to produce such motion. So what does that mean? I mean, it's physics jibber jabber, but what does it mean? Excuse me. Cost. What does all that mean? Friction always does what? Opposes motion, but what if there is no motion?
No friction.
No friction?
No friction.
Really? Like if there's something really heavy and I just kind of push on it like, light, how come it doesn't move? Friction, there's got to be friction.
Oh, I don't know you friction on it.
Yeah, like now, even if I'm pushing on this big counter here, what's holding it in place? Friction. I mean, it's bolted to the ground, but what's really going on? Friction. Friction acts parallel to the surfaces that are in contact and in the direction opposite to the motion of the object or to the net force tending to produce such motion. In other words, if the net force isn't enough, friction is still opposite that net force, right? Like if the applied force is only 10, but there's 100 newtons of friction, it's not going anywhere, is it? Friction depends upon the nature of the materials in contact and their smoothness. Generally, the smoother the objects, the less friction. However, there are some studies, some thoughts that there is a point where it gets so smooth that in fact the friction increases. What might be the cause of that? Any idea? Man, this is a quiet bunch. The objects are so smooth. Well, generally, when you've got like a book here, right, is the book perfectly smooth? I mean, there's a little bit of friction there, right? It slows down pretty quick. There's some air in between, there's some dust, but if you get them so smooth that they are actually microscopically closer together, right, there's actually a pressure. You forced all the air out of it, right? There's actually pressure difference that's causing that. And the molecules are actually attracted to each other at a molecular level. So there is a limit to that smoothness kind of thing. There it is there. Sliding friction is less than or equal to starting friction. Friction is practically independent of the area of contact. This has some controversy associated with it. But if you stop and you think about it, if I've got a book on a tabletop, just like a binder, sitting like this, would that be any more friction than if it was up on its spine, like so? This is clearly about 10 times bigger than this. Same amount of friction. How come? It's an easy answer. Same amount of weight. As long as the face of the book is the same material as this, right? Same amount of friction. Okay? Friction is practically independent. Now, having said that, we all know, being Canadians, if you're on thin ice, what should you do? Spread out, right? Are you reducing friction? No, you're reducing pressure. That's different. So if you want to draw that little picture in there, put the book on end compared to the book flat, right? Same. Starting or sliding friction is directly proportional to the force pressing the two surfaces together. And what causes that? Mass, right? Which is equal to the weight force. M times G. The greater the mass, the greater the normal force. And the greater the friction will be. Which is easier to slide across a floor, a box or a box full of bricks. Which is easier? The empty box, because it weighs less. It's not full of bricks. So the friction is directly proportional to the force pressing the two surfaces together. Do you remember this fine fellow? You don't want to, Hannah. Remember that? Mu equals FF over FN. Where FF is the friction force, and Fn is the normal force. Normal force being equivalent to the weight force as long as it's sitting flat. We're going to adjust that a little bit for great problems. Again, this is the Greek letter M. When you're writing it, you just make a U with sort of a tail on the front kind of, right? And if you walk around Athens, you see that symbol everywhere. Well, because it's part of their alphabet. It's not that they're just sort of rough sort of people, you know. Really? Thanks, man. I got a smile at Riley. You were smiling at that joke. Oh. How would you like to do an example question? How would you like to have it all typed out for you?
Great.
What the heck is this here? Search, rate, and calculator. I think that's someone's.
It's not on here.
No, I got it right here. Don't start writing it down. I edited this for you this morning because it was really bad shape, so I've adjusted these problems here. So here we have an object of mass 10 kilograms, force of 100 newtons applied to it, coefficient of friction between the two surfaces is 0.25, determine the object acceleration. I should point out on the initial handout there, this one here, at the bottom here there's a table of coefficients. In every case, the table of coefficients, you have to have two surfaces. There's no such thing as what's the coefficient of friction for wood. It has to be wood on wood, or steel on rubber, or rubber on asphalt, or something on something. It has to be two. Okay, you can see them there. Generally, coefficient of frictions are decimal values, usually less than 1. If it's greater than 1, there's a good chance that something's goofy's going on. Okay, so here we have an object mass 10 kilograms, force of 100 newtons applied to it, the coefficient of friction is 0.25. Are there units for coefficient of friction? How come there isn't? The answer's in this slide here. How come there's no unit for coefficient of friction? Yeah, it's Newton. It's a ratio. It's newtons over newtons would cancel out, right? It's like pi. Yeah. Okay, so determine the object's acceleration. So to get the object acceleration, I'm going to need F net equals ma. I need F net first, right? What's the first thing you feel like you should do here?
Write everything down.
Okay. Mass is 10. Applied force is 100. The mu value is 0.25, and we are solving for A. I need F net. F net is going to be the applied force plus the friction force. Do I have the applied force? I do. So what's the first thing I need to find? FF. Mu equals FF over Fn. Do you see how I'm sort of going from right to left here? Mapping out my path? How am I going to get Fn?
You started with FA plus FF, right?
I started over here. Oh no, I started here.
Yeah, but no, but after that.
Well, then I went to here.
Yeah.
And I went to here. And I heard someone say, how do I get Fn? FW equals mg. That's my strategy there. That's my plan, right? Now it's a simple matter of just following the blueprints. M times G, so in this case here it's going to be 10 times 9.8 or 98 newtons, right? Ah, good question. Let's do that and see what happens. Are you working in pencil? Are you working in pencil in case I want to erase it?
Oh, why don't you do that?
FF over Fn. Now, technically, if you really want to get sticky here, the weight force is down and the normal force is up, right? So technically, minus 98 newtons is correct for the weight force, Riley, which means that the normal force is, well, positive 98, right?
Why would you throw that negative in there? We went over this last time and it was a big
Yes.
problem. But like, I just, what?
Was it needed in this case? Did we need to know that the weight force is down?
Well, we know.
I mean, we know that, but do we need it in a mathematical sense? Is it gonna matter to a positive and negative kind of thing? Not really, in this case, right? So that's a fine question. You're absolutely right. It's kind of one of those things that we kind of let slide a little bit. Kind of like changing lane. You know when you do your driver's test and they make you do all that lane changing nonsense? And as soon as you're done, you never do it ever again? Kind of like that.
Causes accidents. Oh, no. Like,
Do you have to do it when you're in a big city and there's actually lanes?
you're like, it's like you're actually driving in the parking and you're like, oh, just kidding, coming out. Everyone's like, oh, how you doing? Makes no sense.
I couldn't agree with you more.
I hated doing it.
Yeah, I'm
It
sure
made
you
me
did.
feel so awkward and uncomfortable.
Yes. Okay, so mu equals FF over Fn. 0.25 is equal to FF over 98. So my friction force is a quarter, 0.25 of 98. 24.5. If the box weighed more, would the friction force be more? Like if it was a bigger box, would the friction force be more?
Yeah.
Of course it would, right? Like if it was twice as big instead of 10, if it was 20, well that number would be twice as big, which would make that number twice as big, which would make that number twice as big, right? So yes, if it was a heavier box, a bigger box, the friction force would be more. Listen carefully. Would the frictional coefficient be more?
No.
Jason is quick to say no.
I choose not to.
Who would like to join him on the no island? Oh,
Good.
I'll say it again in case you weren't really sure what I was asking. If the box is bigger, we talked about the friction force being bigger, but would the frictional coefficient be bigger if the box is bigger? Who wants to join Jason on the no island?
Good.
I'm gonna support him.
Good.
Yeah? You're all right if you jumped onto the island. Well done, Jason. Can you explain why?
Because I don't know, friction or the friction code. I can't remember. I don't know why.
I can sense you're almost going to say it.
I can think why in my head, but I can't.
You can't put it in words.
It's like it's almost like the rate at which that.
Yeah, sort of. I mean, if you go back to this list, does this list exist for various masses of boxes? No. Right? The frictional coefficient is how rough rubber on road is, or steel on wood, or whatever it is, right? It makes no difference what the mass is. The 0.25 stays the same. That's why the friction force doubles. So yes, the mu value stays the same. Okay, so now I'm going to throw that into here. And I am kind of scrunching a bit here. My applied force is 100. My friction force is... Now here, does it matter that the friction force is negative?
Yes.
How come?
Would be a different.
Well, it'd be a different number. It'd be, instead of 75-ish, it'd be 125-ish, wouldn't it? So yes, it does matter. Did we get negative here? Or did I just magically put it in there?
You just assume it's
I just magically put it in there. Got it, ladies?
only
Yeah.
on the
So 100 minus 24.5 would be? I think it's 75.5, right?
Sure is.
Now I can throw that in here. Oh, it's so nice when the mass is 10. So my acceleration is... Was that hard? Would you have done that in grade 11? You probably would have, but that would have been like the top of the, yeah.
Why can't we do that again?
Wow.
Stick with it.
You got to grow, you know. You can't just be stagnant in life.
See, I haven't grown for a long time, so I'm.
And it's like,
I do. I just live in my own.
Yeah.
bubble.
Don't change anything.
Don't change.
Who do you think is more resistant to change? Teenagers or people my age?
what's your rate?
But what about the old people?
Okay, well then let me rephrase. Who do you think is more resistant to change? Teenagers, mid-lifers like myself, Quinn, or senior citizens?
The oldies. The oldies.
You know, all my years of working with kids are pretty stubborn about change.
Yeah, but back in my day,
Yeah, I know.
Like, I mean, we used to just pay
Will
for
you be like that?
things with a I get that all the time.
We played with a stick and we liked it.
Yep. And then a movie and popcorn.
Was a nickel.
Oh, I get that all the time.
Okay. Now take the same situation here. Let's put it on a ramp. Ryan missed that whole talk about putting your phone away.
And it's going strong.
Right. Example number 2. An object has a mass of 10 kilograms. Once again, it's placed on a ramp with an angle of 35 degrees. The coefficient of friction is 0.15. Determine the object acceleration down the ramp.
Okay.
Let's draw a picture, shall we? Ryan and anyone else that was away, pay close attention because this is what we did yesterday. Now remember, that weight force right there that I just labeled has 2 components. The one component that acts parallel to the surface, which we labeled FD, with the D standing for down. It's the force down the plane. And then this one here we labeled Fn. Now it's truly not Fn, it's actually the component of friction that is perpendicular to the surface, but it's equivalent numerically to what? The actual normal force. Okay, that was from yesterday, Manny. Okay? We need to determine the object acceleration. Now, is this object going to roll down the ramp or slide down the ramp? We don't actually know yet, do we? Because it might not. Why might it not? The friction might be too much, and in fact, I just made this example up. I have no idea what's going to happen. I am going blind here. You'll notice that I'm working without an answer key. It's like, you know, the tightrope guy with working without a net. What's the first step? What do you think? It's always a good idea to find the weight force, so do that first. $98 newtons. The question is, how do you know whether to put a negative in there? Let's put one in, let's see if it matters.
So it's just not negative, throw us off.
Well, I know the answer, but I want you to figure out whether you need to or not. So let's put it in. I'll put it in a red. Well, then don't put it in until I tell you at the end then. Just watch. Okay, let me do it and you guys not. Okay, fair enough. Okay, so the question is, how do we need to put a negative in there? Riley, what do you think? Should we do it in this case? You learned after the last time. I don't care anymore. Do you remember our new toys from yesterday? FD is equal to mg sine theta. That was one of them. Now this mg has just been figured out for us, right? Now it's okay. Now I'll put it in red. Leave a little space in case you got to put it in later. 98 sine, and the angle here is 35. So 98 sine 35, or I get 56.2. Now, what direction is that? What do you mean by down? You're right. Ladies, this is the part you're asking about. So let's down the ramp. Should that be negative? No, because what way is negative? We've defined negative to be straight down. So this is some sort of weird 56.2 at 35 degrees to the down, whatever. It's just down the ramp, right? If we wanted to, we could define that as negative, and we could define up as positive. And you know what? You're going to need to do that, because in the near future, there's going to be forces pulling this thing up the ramp, and there's going to be gravity pulling it down. Well, we can define that if we want. Okay, so do we want this to be negative? I don't think so, because is there going to be any movement down, like straight down? No. So in this case here, Heather, it doesn't matter. You just, I can't give you a rule. Do it when this happens. I can't. Sorry.
So if it's going up the ramp, then that will be negative.
I would define that as positive, wouldn't you?
No, that's oh.
You can define it any way you want. Yeah. We as a group can agree down means negative, but we as a group can mean down the ramp means negative. If we want, we can define as a group up the ramp means negative. I know you don't like that answer, but too bad.
So if
I can't change it.
If I don't do it.
I didn't say that. I just said you can not like it if you want. There's a big difference.
Okay.
Well, you will. It'll take time. Okay. 56.2, but that's down the ramp, right? Now, so in blue, we've got this FD going down. What's slowing it down from going all the way down fast? Friction. And which way is friction acting? Right? Okay, so what is the friction? Well, friction is based on mu equals FF over Fn. What's the Fn? Oh, our new toy from yesterday. Fn is mg cos theta. They think it's funny when I say it's in my new toy. Battery's not included. You're gonna get T-shirts made? Is that what I heard you say?
I can't feel it away with that. I was just like, let's send it over this year. No. I didn't do it.
80.3 is my normal force. How do I get the friction force? I need to know. I need to know what this FF here is, right? The only way to get that is to use the mu value, 0.15. I get 12 newtons of friction. Okay, now FD down at 56.2. Friction force 12. Which direction is the 12? Oh. Up the ramp or straight up? Up the ramp. You're right. Do we now have to get into a positive and a negative situation here? Yes, because now we got two forces that are in opposite directions. So in answer to Heather's question that she's posting, I guess, I don't know. When do you use a positive and negative? It's when you've got forces that are
Going opposite way.
opposite way, exactly. When you got forces that are opposite to each other, one's got to be positive and one's got to be negative. And I don't care. It doesn't matter which way is positive and negative, really. It's you define it. It's your solution. I don't care. Now,
Just no creativity.
I kind of like my net force being positive, don't you? It just feels weird to have the net force negative. So I'm going to define that as positive and that as negative. Is that okay? Why not? I can do whatever I want. It's my solution. Okay, so that means that the net force is the applied force plus the friction force. Heather, you got to put it away. The applied force, now, okay, actually maybe not. Applied force, is that right? It's not really applied, it's really the FD, right? That's a better descriptor of it. So it's going to be 56.2.
But isn't F not only like equal to MD when there's no friction?
It's not, yeah, but it's not F equal to FD. It's F net is equal to FD plus FF.
How would you know to use FD or FN, or you always use FD? Because you just cast them here.
What forces are acting on this box? FD down the ramp, FF up the ramp. That's it. Net forces add up all the forces, right? FD is down the ramp, yes. It's the part of gravity that pulls it down the ramp. Are we good, Quinn? Okay. I got one last step, I think, right? What am I supposed to be finding here in the end here? Acceleration. Now that I got my F net, remember those good old days in grade 11 when you thought a two-step question was hard? Grade, well, no, there's, oh, the good old days. Yeah, back in my day, a two-step question was hard. We liked it.
Hey, after you want to scroll up so I can just look at that diagram.
Sure.
Just for the fun of it.
Okay. This is probably the hardest question of the day. Well, it should be. It's the last exam, right?
Ooh.
You'll notice that I've left the entire page for it.
I'm not ready for it.
You're not ready for it? Too bad. A box weighing 40 kilograms is pulled along a level floor at a constant speed. Is that important? And not just because I said it in that pause kind of ominous voice there. Why is it important? How do you know? There is no acceleration. Excellent, Ryan. In fact, what does that really mean? When there's no acceleration, it means the net force is zero is what it really means. By a rope that makes an angle of 30 degrees with the floor as shown, if the force on the rope is 260, what is the horizontal component? What's the normal force? And what's the coefficient of sliding friction? So here's one where you're actually finding the mu value. Well, there's my free body diagram. What do you remember about horizontal component? What does it do? Does the thing, says John. Is all of the 260 pulling it sideways? Ryan, is all the 260, this Ryan, up front Ryan, is all the 260 pulling it sideways? No. What is actually pulling it sideways? The horizontal component. This is grade 10 trig. How do I find FH? Anybody remember? 260 cos 30. You guys are getting a little chatty.
You said it was quiet before.
I know. I regret saying that. Thanks. Yeah, thanks, Zach. 225. So of that 260, 225 newtons goes into pulling it sideways. Why did I ask part B? Why do I ask what is the normal force? Because isn't it easy? Isn't it just the weight force?
225.
It is 225. Isn't the normal force just equal to the weight force? Like, what's the big deal? Oh, kill on its own. There's that other thing. Yes, you're right. Most of the time, the normal force and the weight force are balanced. But there's this other thing.
No.
There's a vertical component to that force.
No, why?
Oh, yeah.
Why?
Well, just like every vector has an x and a y component, and just like every rose has its thorn, Every applied force has a horizontal vertical component.
But why have we ever used vertical beforehand?
No, you're right, because I've shielded you from the horrors of the vertical component. But you're all big boys and girls now, and it's time.
I want to use it.
Pretty much always. I've always written the question so you don't have to worry about it. So yes. What do you think that vertical component is equal to? It's a opposite, so it's going to be 260 sine 30 degrees. Anytime there's a force either pulling up or pushing down at an angle, there's a part of that that is acting vertically. So I get 130 newtons. Uh-oh, and I've got big problems now. Because I'm doing math in my head and no, I guess I'm going to be okay.
You can just do that in your head, why you?
No, I'm looking at the next step in my head.
Ow. Just doing things.
I'll show you in a minute, but it's not that hard. You won't be that amazed when I show you. Okay, what does that vertical component do? Is it lifting up
Yeah.
or is it pushing down? It's lifting up, right? So that is like this. In this situation, what's the net force vertically, up and down, Quinn? The net force vertically, up and down, 0. The weight force is balanced by the normal force and the vertical component. The weight force is equivalent to the normal force plus the vertical component. Now, do I have to worry about negatives here? I got forces in opposite directions. Yes. Now,
Are these something we're going to use often, or are we just like making them up as we go?
oh, no. You're going to use this.
Okay.
Okay. Now, you know what? Just to make the sign thing a little bit easier, you're going to hate me for this, but you'd hate me even more if I did it the other way. So I'm going to write F net there. Make that an equals, and can I make that a plus? Can you do that in yours without too much mess?
Oh, why?
I'll rewrite it.
Stop it. Give me a reasoning.
I'll tell you. The F net is equal to the FW. When I get the signs in there, you'll see why. Okay, so the net force vertically we agreed was 0. The weight force, does it matter that it's negative? It's going to be, I didn't actually figure it out, did I?
What? Come on.
Now look all over we are.
Oh, no kidding. It looks
Bring it
like
again. That was cool.
teacher bird. What's 40 times minus 9.8? 396? 392, that's right. Now, negative, does it matter? Oh, yeah.
Stop.
Forces
No.
in opposite directions.
They're canceling.
We're solving for the normal force. What is my vertical component? 130 in the up direction. No? Take those numbers to the side. 392 minus 130 is the normal force. .392 minus 100 is 292, minus 30 is 262. I reduced the normal force. How did I do that? Well, when I was pulling up at this magical angle of 30 degrees, I'm actually lifting the object up. I'm doing some of the work of the table holding the book up. The table doesn't need to work as hard. That will reduce the friction. How come? Mu equals FF over Fn. The mu value was, do I even have it? Oh yeah, that's what we're finding. Oh, now I know what to do.
Erasing it again. What he made.
Oh, okay.
All right.
Any ideas?
Yeah.
Go ahead, Professor Allard.
So you have Fn,
Yeah?
and you need F, right?
I need FF, right?
And it's going at a constant velocity.
Yeah?
So it's equal to Fn.
You're the man.
What? No.
Let me re-explain what Jason just said. Because it's moving at a constant speed, that means that, let me just redraw it here. And I'm doing more work than you would need to. We got a horizontal component sideways. We got a friction force backwards, but the net is 0. How come? Constant speed. Therefore, the friction force is equal to 225.
But then you put F net equals over there, so you're really throwing everyone off here. You said F net equals that.
If you want, if you really, really, really want, I'll let you do this.
I don't want.
Well, I mean, it's actually more descriptive. If you really, really want, you could write F net is equal to FF plus FH. The net force is 0. Friction force we don't know. The horizontal component is 225, which makes the friction force, I guess, minus 225.
I don't want.
I didn't think you would.
No, I do. Otherwise, it's.
Oh, you do want it?
I do.
Oh, okay.
Indeed. Right. So.
Fair enough. Now I can go to what? I'm done now, by the way.
We're done with part one.
Well, we got the last step to do. We can see the light. We can ease up. Friction force, do I need the negative 225 there? No, friction coefficient's negative, never negative. Normal force, be careful, normal force 262. .86. Ooh, that's kind of rough. Because it's a high number. The number's close to 1. It's a rough surface.
Oh, so that number's high is the roughness?
Yeah. The rougher it is, the greater the coefficient of friction.
I didn't know that.
Yeah. How much would some mess like that be worse, do you think? 1, 2, 3, 4, 5, 6. Yeah.
Included some formulas.
Probably 6. Basically, there's 6 steps there. I would say. Okay, did I include? I did. Excellent. I've taken up a lot of your time today. Thank you for your patience. There are some sort of reading questions there. There are some word problems there. There are answers on the back and a QR code for solutions. So you're set. I will give you tomorrow's period to work. We will probably do some textbook examples on Monday. We have to do a lab, our first one. We will actually determine the frictional coefficient of wood on wood.
Great.
That will be Tuesday's plan.
So excited.
It is exciting. Okay.